I want to spend a little time talking about how we can use antiderivatives to model physical problems, so things that really happen. And I want to illustrate that with an important example relating position and velocity. So if I thought about some object that I'm going to throw up in the air, that position, the height of that object changes in time. So imagine we're in class and I actually threw something in the air and it goes up and then it comes down. And so at every instant in time I have a height. And so I'm going to let h represent the height of the object, and time I'll represent with the variable t. And every value of time there's a corresponding height. And so I have an example of a graph. This graph is an example of a possible height as a function of time. So we've got at every instant in time there's a different height. If I asked you for a time like 0.5, I could go to the time of 0.5 and I could go to the data, and the data would tell me what my height is. So we have height as a function of time. Now, the derivative represents the rate of change, or the slope. So at any given point, again, I wanted my other color. So if I have at time 0.5, I'm up here at this height. The height is the height, or the value of the function. The derivative, or the rate of change, is the slope of the tangent line, right? And so at every point on this graph, there's a different slope corresponding to a different value of the derivative. And that derivative is represented by the velocity. Whenever we talk about velocity, it's the rate of change of position. Here is the rate of change of my height. Okay, so we've been talking about antiderivatives, which means if I have a derivative, I can go and find the original function. So in the context of position, if we record the velocity, right? Like if I'm in a car and I'm tracking my speedometer, I know exactly how fast I'm going at every instant. Or somehow, as this object, this ball I throw in the air, if I can track how fast it's moving through the air, rather than the height, I'm tracking the velocity, I now know the derivative. So if I could find an antiderivative of that function, I would have recovered the height, except I wouldn't know the constant I need to add. So we're going to look at some examples where we're given a derivative. First we'll look at velocity, and given that velocity, we're going to find our height as a function of time. So here's our example. We're recording the velocity, and our units are feet per second, right? So we have units. It's a unit of speed, a distance over time. It's the rate of change of position. And we record that. We're recording its vertical motion, so the velocity vertically. And we're going to measure it as a function of time, and we're going to record time also in seconds. And it's important that these units, the units of time in the rate of change and our variable, match. If they don't match, I have to do a change of units, right? A conversion. Okay, so here's our setting. We're told the height is 40 feet after 1 second, and the velocity, if I looked at the velocity as a function of time, I have this function. All right, let's summarize what we have. I've got the height, so we've got some data. When the time is 1, our height is 40. And we also know the velocity, which is, here's an extra piece of information. We're now responsible to know that's the rate of change of height, the derivative, is equal to 48 minus 32t. So at every instant in time, I can calculate my velocity. For example, at time t equals 1, I can figure out how fast I'm moving. It's 48 minus 32 times 1. 48 minus 32 is 16. I'd be moving at 16 feet per second, right? But I don't know it just at time 1. I know it for all time. I have a formula. All right. So the connection of antiderivatives and derivatives is if I know the derivative, my height must be an antiderivative of my velocity. So what I'm going to do is I'm going to do an integral to find the antiderivative of 48 minus 32t. Now, integrals always need the variable's differential, the dt, right? It's a rate times a time. A little velocity times a distance, a little velocity times an amount of time multiplied together gives me a distance traveled. Okay, so now we've learned how to find antiderivatives. So 48 minus 32t has an antiderivative of 48t. 32t has an antiderivative of 32 over 2, so that's going to be 16t squared, right? But there's one more thing. Indefinite integrals need a constant. So this is my height as a function of time. The complication is we don't yet know what is the value of c. And this is where we're going to use our initial information. So we'll use the data to find c. All right, what do I mean by that? Well, our height, we have a formula, and our height, we have a table. So what we'll do is we're going to substitute t equals 1, height equals 40 into this equation. And so the height, h, equals 48 times t, which is 1, minus 16 times t squared, which is 1 squared, plus a constant that we don't know. And we're going to solve for c. 48 minus 16 is 32, so 40 equals 32 plus c, and we discover that constant is 8. Okay? And so we're going to substitute that constant into our formula, and that gives us our final value. Let's find a space we can put that. Let's do maybe something orangey here. My height is 48 times t minus 16t squared plus our constant 8. So our initial value, our data, that allowed us to determine the constant, and that gives me now my height as a function of time. We now have a formula, and we could calculate the height at any time. As our second example of using an antiderivative to find or solve an applied problem, I wanted to tell you about someone here at James Madison University, Dr. Roshna Wunderlich. She's in the biology department, and she studies the mechanics of motion, and in particular, one of the things she studies are lemurs. So she has done some research where they use accelerometers. These are devices that can track how things are moving, and the way they do that is they measure how something accelerates. So she's strapped these accelerometers to the bodies of lemurs, and then she records them as they leap, as they jump. So what I wanted to do is I wanted to talk about how we can use accelerometer information, acceleration, to be able to find other information. Well, what is acceleration? Acceleration is a rate of change of velocity with respect to time. That means that our acceleration is a derivative. So if I know my acceleration, then I can find velocity, right? My velocity is an antiderivative of my acceleration function. So we're going to integrate our acceleration to find our velocity. Well, if I know velocity, velocity is itself a derivative. It's a derivative of my position or my height. So if I'm recording the vertical velocity, then I can calculate the height as the integral of my velocity. So if I start with my acceleration, I can calculate velocity. Once I know velocity, I can calculate, sorry about that, once I calculate velocity, I can calculate my position. Now each time I calculate an antiderivative, there's going to be a constant of integration that I'll have to find. So I have to know something initially, or some data point about each variable. When I integrate acceleration, I'll need to know a velocity at some starting time. Alright, so let's take a look at an example. Now I don't have any data from an accelerometer to work with, so we're going to use a function with a formula. Here's an example of something that we might have. Pretend I have an accelerometer and we've recorded 1 second worth of data, and so our acceleration for the first quarter second, here's our first quarter second, time is between 0 and a quarter. We have that my acceleration is 20 times time. Right, that's a linear graph. In fact, let's draw a little graph here. Right, here's my time, here's my acceleration. So here's a quarter, 3 quarters, and so between the times 0 and a quarter, I'm going to have a straight line. Let's see, at a quarter I get up to 5, so here we are at 5. I've got this line. Between 1 quarter and 3 quarters, I stay here at this constant acceleration, and then 20 minus 20t is such that I come back down to 0 when I hit time 1. So this is my acceleration function. I can now calculate my velocity because the velocity is an antiderivative of acceleration. So, on each interval, we can calculate our velocity. So let me write that down. Velocity is going to be an antiderivative. See, let me write. It's an antiderivative of acceleration. So we integrate acceleration, and we will be integrating each of the 3 formulas. So, on this first interval, my acceleration is 20 times t. The integral of t is 1/2 t squared. And so I'm going to have 1/2 of 20 is 10 t squared plus some constant. Each time we do an integral, we'll have a different constant. So let's call this one constant 1. And this is for that first quarter second. The next piece, the acceleration was 5. So when I integrate that, I get 5t plus an integration constant. We'll have a different one. We'll call it c2. So this is between a quarter and 3 quarters. And then finally, on that last piece, we're going to integrate 20 minus 20t, and I get 20t minus 10t squared plus yet another integration constant. We'll call it c3, and that's for our last interval of time. Now, what do we know? We have some data that the velocity is 5 meters per second when t is 0. And that happens to apply in the first rule. We can calculate C1 by using that data. What we'll do is we'll say my velocity is 5, and that's supposed to equal 10 times 0 squared plus C1, and 0 squared is 0, and so I get that my C1 is the value 5. Okay? So we have found our first constant. Now, we have 2 more constants we need to find, C2 and C3. The way that we're going to do that is we're going to require that the velocity is continuous at the breakpoints. So at a quarter, these two formulas need to agree. So we can calculate when t equals, actually let's do it in the orange, when t equals a quarter, if I use the velocity from the first formula, I get 10 times a quarter squared plus 5. So let me quickly calculate that. And I get 5.625. And now I can use that data in this second equation. So using the second equation, I get 5 times a quarter plus C2 is supposed to equal 5.625. And I can solve for C2 and get 4.375. Now that I know C2, I can use this equation because my value at, let's change a new color, maybe blue, right? At a quarter, or 3/4, I have two formulas, and I can use my initial condition at 3/4 to calculate C3. So why don't you see if you can do it? Pause the video, calculate it, and then check your work. So I use the second formula with t equals 3/4, and I get a value, my velocity is 9.375. And now what I'll do is I will go back and I'll say, alright, I want to calculate the formula using the other velocity, or the third rule. So I put in 3/4 in for time on that rule, and I should equal the same velocity. And now I can calculate and solve for C3. Alright, so when I did this, I found C3 equals 0, and something wasn't right. I went back and I looked through my earlier results, and I see that I made a mistake. So when I found my C2 of 4.375, I should have used it in my place of C2. That was a mistake. So let's fix that work. We want to change that back to 4.375, and that will update my value to 8 1/8, so 8.125. Okay, and so we want to solve this where this new formula also gives me 8.125. Okay, and now if I calculate my C3, I get that C3 should have been equal to negative 1.25. Alright, so let me clear some space. I'll summarize these results. So now that I have my formula for my velocity, what I could do is I could take each of these formulas. Oops, still erasing. Don't want to do that. We can put each of these formulas into a graphing calculator, for example. I'll put this into Desmos and use these intervals for a piecewise function, and I can take a look at the graph and see what it looks like. Well, here's what we get when we go to Desmos. So here's what I've done. I've used a piecewise function, and the way I do that in Desmos is I use curly braces. And first you put the inequality, so between 0 and a quarter, I'm going to use the formula 10x squared plus 5. On the next interval, between a quarter and 3/4, I'm going to use 5x plus 4.375. And on the last interval, 20x minus 10x squared minus 1 1/4. Now, the reason I found that there was a mistake is when I tried to graph this, this last segment was shifted up too high. It wasn't continuous. So I knew I had made a mistake. Because when we find our antiderivative, we needed it to be continuous. Okay, now we've done enough on this example, but now that I have my velocity, that's the derivative of my height. And so I could find an antiderivative of this. I could go through the same process, and I would get a height function. So this is how I might take data from an accelerometer, which tells me acceleration, integrate it to find velocity, integrate it again, and I get my height. And this is something that I could use to really find information that could be useful in my research. Alright, so that's how we can use antiderivatives to solve physical problems, by using initial data to calculate the constant of integration that's applicable for the data that we're given.